Let's start with this piece of Java code. I have a string variable sample to which I'm assigning a string, which I get by invoking getSampleData method on helper class. Essentially, it is returning some alphanumeric string. Then I have a string that represents a rupee symbol. I am concatenating the initial alphanumeric string with the rupee symbol, and the result is stored in a variable called another. Then I am printing the lengths of both sample and another. Finally, I'm just printing done. So let's run this program. See, it is run. Let's see what is the length. So the initial the length of the initial variable, that is the sample, is 10,48,581 or 1,048,581. That is the number of characters in the string sample. Then when I add rupee symbol, it is essentially adding one more character, that is the length is one more than the first. Now, to understand how much memory these strings take, let's debug this. For that, I'll put a breakpoint in line number 8. Let me debug this. Let's go to this part of the code to see what it is. So initial string sample, it is occupying 10,48,581 bytes or 1,048,581 bytes. What we'll do is we'll go to this another variable, right, and see it's occupying 20,97,164 or 2,097,164. So just by adding rupee symbol, or just to add rupee symbol, it took more than 1,000,000 bytes of memory. So is storing rupee symbol that costly? Does it require more than 1,000,000 bytes? Let's find out in this episode of Evolving Code. Hello and welcome to Evolving Code. My name is Naresha. In this episode, we will look at the evolution of string representation in Java. That is, we will look at how string data type internally represents its data and how that representation evolved over Java versions. And in this part 1, we will look at the memory footprint implications of this change in representation. The initial version, what you saw, was running on Java 11. I have switched back to Java 8 to start with, to understand how initially string class used to represent its data internally, that is in memory. So let's run the code once to make sure it's running fine. Look at you get the same output as you saw before. Let's put the breakpoint here, and let's debug now instead of running it. Let's go to the most important part, what we need here. We would see I have a sample which takes 1,048,581 characters. In this case, we are in Java 8, and another which takes 1,048,582. that is one character more than sample. And if you look at rupee, it took character of 1. What does that mean? It means that string up to Java version 8 under the hood used character array to represent or to store its data. I will open the source here. So we are in a string class, and you would see the value, that is the characters in string, are stored in character array. That's how Java used to store characters inside string up to Java version 8. And I hope you would already know that each character, it's UTF-16, so it would take 2 bytes of memory. So the total memory taken would be twice the number of characters. Let's switch to Java version 11 and see what happens. In fact, this change was done in Java 9, but let's use the next LTS version of Java, which is Java 11. We are using Java 11 now. Let me just run it once. Java 11, and let's debug and see what we see here. You see sample, it's a byte array now, and we'll see exactly what we saw in the beginning of this episode. So initial one takes more than 1,000,000 bytes, rupee symbol takes 2 bytes, and another string takes more than 2,000,000 bytes. So I hope now you understand what's going on here. Initially, say you look at the character, the 2, which is represented as using the byte value 50. The same byte value here, it becomes 50 comma 0. That is, instead of 1 byte, it is now taking 2 bytes. So every character in the alphanumeric string previously required only 1 byte, now requires 2 bytes, because I have, if you consider the entire concatenated string, I have one value rupee which cannot be represented in 1 byte. It requires at least UTF-16 character set, and whereas the simple alphanumeric values are simple ASCII characters, so they can all be stored in a single byte. So what Java does from Java 9 onwards, if at all it's a simple ASCII character, Java will make you, if the string contains only simple ASCII characters, Java will use 1 byte per character. If at all there are any characters which require UTF-16 character set more than 8 bytes, then the entire characters in the string will be represented using 2 bytes. Here we have the summary of the data type representation inside Java class string. So previously you could see on Java 8 it's a character array, and from Java 9 onwards it becomes a byte array. So what benefits do we get from this is the reduced memory footprint. If you have a very large string in your application, and those strings contain only simple ASCII characters, then you will have up to 50% reduction in memory footprint. If you have already worked on a lot of projects in Java, I'm sure you understand how frequently string data types are used. So for many applications, this would be a huge benefit. The amount of memory required to run your application can be significantly lower if you use a lot of strings that contain only ASCII characters. So that's the fundamental benefit of this. This feature is called compact string. in Java, and this particular change was proposed under JEP, that is Java Enhancement Proposal 254. But what are we sacrificing, or what are we trading off to get this benefit of reduced memory footprint? We will explore that in the next part. I hope you learned and enjoyed this episode. See you in the next episode. Have a nice day. Thank you.